Video covers Section 4, State Types. Finite state machines can express an algorithm as a number of states, their relationships, and their input and output. Remember, states are elements in your state machine. Individual states can make decisions based on their input, perform actions, and pass output to other states. States can perform a variety of functions in your state machine. A task state does some work in your state machine. A choice state makes a choice of which branch to run. A fail or succeed state stops running a state with a failure or success. A pass state passes its input to its output or injects fixed data. A wait state provides a delay for a certain amount of time or until a specified time and date. A parallel state begins running parallel branches. Finally, a map state dynamically iterates steps. In this section, we'll take a closer look at each of these state types. Tasks do all of the work in your state machine. A task performs work by using an activity or a Lambda function, or by passing parameters to the API actions of other services. The Amazon States language represents tasks by setting a state's type to task. It also provides the task with the Amazon resource name, or ARN, of the activity or Lambda function. An activity consists of program code that waits for an operator to perform an action or provide input. You can host activities on Amazon Elastic Compute Cloud or Amazon EC2, Amazon Elastic Container Service, also known as Amazon ECS, or even mobile devices. Activities pull step functions by using the getActivity task, sendTaskSuccess, sendTaskFailure, and sendTaskHeartbeat API actions. Step functions can invoke Lambda functions directly from a task state. Step functions also integrates with some AWS services, including the ability to directly call and pass parameters to the API of those services. You can use step functions to coordinate these services directly from the Amazon States language. This slide shows two examples of the task state. The first example performs an activity named Hello World, which is identified by the activity ARN in the resource field. The second example performs a Lambda function, which is identified by the Lambda function ARN. A choice state adds branching logic to a state machine. A choice state must have a choices field whose value is a non-empty array and whose element is an object called a choice rule. A choice rule contains a comparison and a next field. A comparison is two fields that specify an input variable to be compared, the type of comparison, and the value to compare the variable to. The next field value must match a state name in the state machine. In the example, the first choice rule checks whether the numerical value is equal to 1. The second choice rule checks whether the numerical value is equal to 2. Note the $ symbol in these examples indicates a variable. You might see this in the other state examples. This slide provides examples of a succeed state and a fail state. A fail state stops running the state machine and marks it as a failure. This state requires the type field to specify the state's type. In addition, the fail state offers two optional fields, the cause field and the error field. The cause field provides a custom failure string that can be used for operational or diagnostic purposes. The error field provides an error name that can be used for error handling, operational, or diagnostic purposes. Because fail states always exit the state machine, they don't have a next field and don't require an end field. A succeed state stops running a state successfully. This state is a useful target for choice state branches that don't do anything except stop running the state. Because succeed states are terminal states, they don't have a next field and don't need an end field. A pass state passes its input to its output without performing work. Pass states are useful when constructing and debugging state machines. This example shows a state machine that consists of a single pass state. When this state machine runs, it injects some fixed data, which might be useful for testing purposes. A wait state delays the state machine from continuing for a specified time. You can choose either a relative time specified in seconds from when the state begins, or an absolute end time, which is specified as a timestamp. In this example, the wait state introduces a 10-second delay into the state machine. The parallel state creates parallel branches in your state machine. A parallel state causes step functions to run each branch, starting with the state named in the branch's start at field as concurrently as possible. The service waits until all branches reach a terminal state before processing the parallel state's next field. A branch can fail because of an unhandled error or by transitioning to a fail state. If a branch fails for either reason, the entire parallel state is considered to have failed, and all of its branches are stopped. You can use the map state to run the same set of steps for multiple elements in an input array. The iterator field is required. This field's value is a reference path that identifies where in the effective input the array field is found. In this slide's example, the iterator is the input path field. Let's look at some key takeaways from this section of the module. Individual states can make decisions based on their input, perform actions, and pass and manipulate output to other states. Add branching logic to a state machine by adding a choice state. Run multiple functions concurrently by using the parallel state. Succeed and fail states do not require an end field. Thanks for watching and see you in the next video. This video covers Section 5, Step Functions Use Cases. Step Functions has two workflow types, Standard and Express. You define your state machine by using the Amazon States language, regardless of your workflow type. However, the state machine execution behavior will vary based on your choice of standard or express workflow. Standard workflows are ideal for long-running, auditable workflows. Because of their ability to show execution history and visual debugging, the full execution history of a workflow can be retrieved by using the Step Functions API for up to 90 days after your execution has completed. Standard workflows have an exactly once workflow execution, which means they never execute more than once, unless you have specified the retry behavior in ASL. Therefore, they are suitable for non-idempotent actions because their executions always result in a change of state. Express workflows are ideal for high event rate workloads such as streaming data processing and Internet of Things, or IoT, data ingestion. Two types of express workflows are available, asynchronous and synchronous. Asynchronous express workflows have at least once workflow execution, and synchronous express workflows use an at most once workflow execution. Express workflows can run for up to 5 minutes and are billed based on the number of executions, duration of execution, and memory that is consumed. Step Functions provides functionality for a variety of use cases, such as processing data, automating tasks, modernizing monolithic applications, orchestrating applications, transcoding media files, and sequencing batch processing jobs. Step Functions is also commonly used to send messages from automated workflows, publish events from serverless workflows, coordinate container tasks in microservices and serverless applications, access databases from serverless workflows, sequence steps of machine learning, also known as ML, workflows, and coordinating extract, transform, and load, also called ETL jobs. These use cases can rely on standard or express workflows, depending on their requirements. In Step Functions, activities are a way to associate code that runs somewhere, referred to as an activity worker with a specific task in a state machine. An activity worker can be an application that runs on an EC2 instance, Lambda function, or mobile device. Basically, it can be any application that can make an HTTP connection, and it can be hosted anywhere. When Step Functions reaches an activity task state, the workflow waits for an activity worker to pull for a task. An activity worker pulls Step Functions by using the getActivityTask API action, and it sends the ARN for the related activity. GetActivityTask returns a response, including input, a string of JSON input for the task, and a task token, a unique identifier for the task. A task waiting for a task token will wait until the execution reaches the 1-year service quota. It relies on a heartbeat threshold, which is specified the state machine's ASL definition. After the activity worker completes its work, it can provide a report of its success or failure by using send_task_success or send_task_failure. These two calls use the task token to associate the result with that task. One common use case for activities is to manage a workflow that has a manual approval step, such as a promotion approval. In the slide example, Amazon CloudWatch invokes Lambda on a schedule. Lambda, the activity worker, pulls Step Functions for an activity task by calling getActivityTask. First, Lambda successfully calls the API action. Next, the activity is vended to Lambda as a string of JSON input for the task and a task token for callback. Then, Lambda calls the Amazon Simple Email Service, or Amazon SES messaging service. The messaging service sends an email notification to a manager to either approve or deny an employee's promotion. The response is recorded as either a success, approve, or failure, and is sent as an API request to Amazon API Gateway. API Gateway calls either send task success or send task failure and uses the vended token. The JSON for the activity state machine for a manual approval process might look like this slide. In this example, the state type is task, and the activity ARN is provided as a resource for the task. This diagram depicts the flow of a step function state machine that is used for automated and continuous deployment of Amazon SageMaker models with step functions. The dashed arrows highlighted in pink are instances where the state machine must pull and wait for a task to be completed. Let's look at some of the key takeaways for Section 5. Activities are a step functions feature that associated code with a specific task in a state machine. A task token is a token that represents a specific task that step functions generates when a task is assigned to a worker. An activity worker can run on any application that is able to make an HTTP connection. Thanks for watching, and see you in the next video.
Welcome. In this video, I'll show you how to create a state machine using AWS step functions to invoke an AWS Lambda function. I'll create some routing logic so that the state machine will act as a basic calculator. Okay, let's get started. First, I'll head over to the Lambda console. I'll search for Lambda in the service search box and select it. Next, I'll open the existing Lambda function named calculator function. Let's examine what this function does. Notice that it is a basic function. It expects 3 values. The first value is the operation, and the next 2 values are the numbers, and those will be the 2 numbers to perform the operation on. All 3 of these values are stored as variables, and as you can see, the function either adds, subtracts, multiplies, or divides the 2 numbers depending on the operation supplied. Finally, the function will return the result of the calculation. Next, I'll head over to the step functions console. I'll open it in a new tab. Here, I'll choose Create State Machine. I'll choose to design it visually, and for the type, I'll choose Express and then Next. Here you can see the Step Functions Workflow Studio interface. I'll design a state machine to invoke the Lambda function that we were just looking at. Let's start by adding a choice action, because a user who uses the calculator will need to decide if they want to add, subtract, multiply, or divide 2 numbers. I'll choose Flow here in the left panel and drag the choice statement onto the canvas. I'll give it the name Evaluate Operation. Next, with the choice state selected on the canvas, you see that the configuration panel displays to the right. Let's configure 4 rules for this choice state in addition to the default rule. I'll choose Add New Choice Rule and will then choose Close 4 times. These will be rule number 1, rule number 2, rule number 3, and rule number 4. Next, I'll go to the Actions menu. Recall that I want to invoke a Lambda function. That is actually a very popular use of step functions. The action is right here at the top. I'll drag it onto the canvas to rule number 1, and I'll name this one Add. I'll also specify that it is the calculate function that should be invoked. Next, I'll drag the Lambda invoke action to rule 2, and I'll name this one Subtract. Again, I'll specify that it is the calculate function that should be invoked. I'll drag another one to rule 3, and this one will be named Multiply, and we'll again invoke the calculate function. And finally, I'll drag a 4th one to rule 4, and we'll name this one Divide, and again, this will invoke the calculate function. So you can see that I have a different path specified for each possible operation. However, I still need to specify a condition for each path. I don't want all 4 paths to be followed every time the state machine is invoked. Let's take a quick look back at the Lambda code. It says if the operation equals add, then add the 2 numbers. Okay, so let's return to the State Machine tab and configure a condition for rule number 1. In the variable field, I'll enter $.operation as is equal to the string constant and add. I'll save the condition. Great. Now the state machine will follow the path to rule number 1 only when the operation is add. Notice that the choice state now shows a message that the rules must be valid choice rules. Because I just added a condition to one of the rules, the choice state is now indicating that the other rules I created must also be configured so that they are valid. I'll configure similar conditions on the other three states. Rule number 2 gets the condition $.operation as is equal to string constant and sub. Rule number 3 gets the condition $.operation as is equal to string constant and mul. And rule number 4 gets the condition $.operation as is equal to string constant and div. Notice now that the choice state is no longer complaining about missing or invalid rules. The lambda function performs the actual adding, subtracting, multiplying, and dividing logic, but recall that the function will then return the result. I'll need a way to capture this, so that is what I'll configure next. I'll return to the flow tab and add a pass state. I'll place it in between the add state and the end state. I'll name the pass state display result. Next, I want to make all 4 rules that will invoke lambda have the display result state as their next step. If I choose the add state, you can see that it has already set the next state to be display result. I'll choose the subtract state and we'll set that, and I'll configure the display result to be the next step for the multiply state and the divide state as well. Next, I want to have a way to handle an unknown operation value. I'll return to the evaluate operation and highlight the default rule. Next, I'll choose the flow tab and I'll drag a fail state onto the canvas. Let's name it error, and for cause, I'll enter invalid input supplied. Okay, the logic is now in place. I'll choose next, and here you can see that everything I've configured in this Workflow Studio interface is creating a JSON document in the background. This Amazon States language, or ASL document, defines how the state machine will function. I'll choose next again. Let's give it the name Simple Calculator. I'll leave all the other default settings, and finally I'll choose Create State Machine. Excellent, now I have a state machine. I'll give it a test. I'll choose Start Execution, and here in the input area, I'll replace the existing JSON with this JSON document that I'll paste in. As you can see, this should perform an add operation on the numbers 150 and 75. I'll start it, and it looks like it's completed successfully. I'll expand the details, and as you can see, the output is 225. That looks correct. Let's try another operation. I'll paste in the same JSON input, but this time I'll change the operation to div, meaning divide, and run it. Great, that operation worked as well. I could continue testing the other operations as well, but you get the idea. In summary, you've seen how to use step functions to invoke a lambda function. I've demonstrated a very basic data processing example, and you've seen how you can configure branching logic in the state machine so that a different path is taken based on the input data. That concludes this demonstration. Thanks for watching.
Now time to review the module and wrap up with a practice certification exam question. In this module, you learned how to recognize the dynamics of workflow coordination in distributed applications, describe step functions, identify state types, indicate common use cases for step functions, and recall step functions API operations. Now let's take a look at a sample exam question. When a customer submits a request for a credit limit increase, the request is to be processed automatically by comparing the request to their credit limit. If the request is more than their pre-approved credit limit, step functions must send the request to a manager for approval. Which type of state should be used to accomplish this process? A, parallel, B, choice, C, task, or D, pass. Note the key requirements stated in the problem. The process needs to compare the requested amount and pre-approved limit. It needs to be sent to a manager for approval if the request is more than the pre-approved limit. consider the answer choices, and rule them out based on these requirements. We'll pause a few seconds before discussing the correct answer. If you need more time, consider the answer choices, feel free to pause the video. So, how do these answer choices compare to the requirements? For the first choice, the parallel state doesn't provide the option of input. It simply runs two functions at the same time. The second choice, the choice state, provides the ability to enter manual input if a choice needs to be made. This meets the requirement to have manager approval if the request is more than the limit. The third choice, the task state, also does not provide the ability to inject a manual input. The final option, the pass state, simply passes the input to its output without performing any work. This will not allow the request to obtain manager approval. The correct answer is B. Using a choice state, you can have step functions make decisions based on the choice state's input. That concludes this module. Thanks for watching. We'll see you in the next video.
Welcome to Module 12, Developing Secure Applications on AWS. We'll begin with Section 1, Introduction. At the end of this module, you should be able to list two aspects of securing applications. Recall how to authenticate with the AWS Security Token Service, also known as AWS STS. Describe how to build secure applications with Amazon Cognito, and secure part of a website with Amazon Cognito. In this module, you'll learn about securing network connections, authenticating with AWS STS, and authenticating with Amazon Cognito. Sophia wants to modify the Cafe website to provide a login for Cafe employees that gives them access to features that aren't available to external users. Sophia doesn't have much experience with authentication and authorization. Faith, an AWS developer and Cafe regular, suggests using Amazon Cognito. The service is easy to set up and integrate with the AWS services that the Cafe website uses. The diagram on this slide gives an overview of the application that you will build through the labs in this course. The highlighted portions are relevant to this module. As highlighted in the diagram, you will use Amazon Cognito to provide a login for Cafe employees that gives them access to features that aren't available to external users. This example AWS architecture illustrates the layers of a web-based application. Recall that with the AWS Shared Responsibility model, AWS is responsible for the security of the cloud, and you are responsible for security in the cloud. Developers must consider security of an application at many levels. Previously, you learned about two services that are core to AWS security. The first is Amazon Virtual Private Cloud, or Amazon VPC. This service helps you to secure your networks and subnets and protect your AWS resources in the cloud. The second is AWS Identity and Access Management, or IAM, which helps you control access to AWS resources through policies that grant permissions to users, groups, and roles. In this module, you'll learn about two aspects of applying security of your application. The first aspect is securing network connections over the internet between application clients and the servers hosting your application. The second is controlling user access to AWS resources that your application calls. Thanks for watching. We'll see you in the next video. Cover Section 2, Securing Network Connections. Transport Layer Security, also known as TLS, and its predecessor, Secure Socket Layer, also known as SSL, are open standards that use public and private certificates to establish the identity of websites over the internet and resources on private networks. SSL and TLS protocols also encrypt network communications between connected resources. For example, Amazon.com uses TLS for all traffic on its website, and AWS uses TLS to secure API calls to AWS services. HTTPS connections might use either SSL or TLS. Although the term SSL is still widely used, TLS is typically being used to secure the connection. In this example, Elastic load balancing simplifies the process of building secure web applications by terminating HTTPS and TLS traffic from clients at the load balancer. The load balancer encrypts and decrypts the traffic, instead of requiring each Amazon Elastic Compute Cloud or Amazon EC2 instance to handle the work for TLS termination. You can configure Amazon CloudFront to require that viewers use HTTPS so that connections are encrypted when CloudFront communicates with viewers. You also can configure CloudFront to use HTTPS with your origin so that connections are encrypted when CloudFront communicates with your origin. CloudFront performs SSL TLS negotiation between the viewer and CloudFront, and between CloudFront and the origin if the response is not already cached. In this example, you might set up an origin access identity, also called an OAI, in CloudFront. The OAI can have Amazon Simple Storage Service, or Amazon S3, bucket permissions, so that only CloudFront can access the bucket through the OAI. This means that users cannot directly access content on the S3 bucket even if they have the URL. Certificate authorities, also known as CAs, issue certificates to specific domains. When a domain presents a certificate that a trusted CA issued, your browser or application knows it's safe to make the connection. The steps listed in the slide show how the TLS and SSL protocols use the certificate to ensure that the client connecting is a trusted resource. First, the CA issues a certificate to the server. Next, the client requests identification from the server. In response, the server sends its certificate and public key to the client. The client determines if the issuing CA is trusted, and if it is, sends an encrypted session key to the server. The server sends an acknowledgement, encrypted with the session key, to the client. All data sent from the client to the server is now encrypted with the session key. Managing your SSL TLS certificates presents several challenges. The first is security. Certificates can be vulnerable for many reasons. For example, certificate name mismatch, use of internal names, missing or misconfigured fields and values, outdated or weak hashing algorithms, weak keys, and weak cipher suites that compromise SSL endpoints. Finding and fixing these vulnerabilities can be challenging. The second challenge is discovery. Manually gathering details about all the individual certificates in your network is not practical when you have hundreds or thousands of them. Rotations and renewals are other challenges. Manually managing certificate expirations is prone to error and could cause you to miss rotations and renewals. Another challenge is authorization. You need to be able to verify that someone is authorized to approve and issue a certificate. Finally, cost. Managing certificates can be expensive. You must pay a fee to validate certificates. You must also consider support costs, legal costs such as insurance and warranties, ownership or control costs such as fees for root embedding, and infrastructure costs. With AWS Certificate Manager, also known as ACM, you can provision, manage, and deploy public and private SSL and TLS certificates for use with AWS services and your internal connected resources. ACM removes the time-consuming manual process to purchase, upload, and renew SSL and TLS certificates. With ACM, you can quickly request a certificate and deploy it on AWS resources integrated with ACM, such as ELB load balancers, CloudFront distributions, and APIs on Amazon API Gateway. ACM manages certificate renewals. You can also create private certificates for your internal resources and centrally manage the certificate lifecycle. Public and private certificates provisioned through ACM for use with AWS services are free. You pay only for the AWS resources you create to run your application. By making it easy to enable SSL and TLS, ACM helps organizations meet regulatory and compliance requirements for encryption of data in transit. Here are some key takeaways from this section of the module. You can encrypt network communications with SSL and TLS protocols. SSL and TLS require a certificate issued by a certificate authority also known as a CA. ACM simplifies management and renewal of certificates. Thanks for watching. We'll see you in the next video.